Okay. So again, this week we're not learning anything new. We are going to deal with more problems in which we are asked to balance chemical equations, and we're going to do this with a greater variety of different types of reactions. All right? So the first slide I'm going to present to you, you can choose whether or not you're going to write down the first 2 points. It's the last slide we went over last week. How do we balance chemical reactions? Again, the first 2 points, what we ended with last week, and then I added another point. So first, the law of conservation of matter tells us that matter cannot be created or destroyed. This is what influences our desire to balance chemical equations. Because if we cannot destroy matter, an atom of oxygen cannot disappear, right? Every atom of oxygen that is in one of our reactants has to appear in one of our products. Every atom. We cannot destroy matter. We cannot destroy these atoms. And we cannot create atoms. We can't have something show up in our product with no idea of how it got there. Okay? Right? We talked about chemical reactions, and chemical reactions are processes that involve atoms moving from one molecule to another. Right? But these atoms, they're moving, they're not disappearing, and they're not coming from nowhere. We should be able to trace where they came from. Okay? So again, this is what motivates us or drives us to balance chemical reactions. I mean, plus, it's just awesome, right? Who doesn't love balancing chemical equations? And so that alone should motivate us to balance them. Okay, so again, to reiterate this point, the number of atoms of each element must be the same on both sides of the reaction. No matter what the element is, the number of atoms better be the same on both sides of the arrow. I know we'll get into nuclear reactions and we'll have atoms start to deteriorate, but then they will change from one atom type to another, and we will keep track of the protons, neutrons, and electrons. All right, this is something I told you last week. I did not write it on the slide. I just want you to remember that it's helpful if you start with the most out of balance element. There are a couple of other points that I'll make as we work through balancing these chemical equations. And they'll pick up on the recording, but they're not actually in the writing. So how should we answer this question? How do we balance chemical reactions? You can answer it saying something like this. See what follows. S-E-E. What follows. Or you can answer it like this and just answer it saying look and see. Look and see. Okay, that's right. Okay, look and see, or see what follows, because then we're going to go through and we're going to balance some chemical equations together. All right. No key terms from this question. And so if you miss those, because we're not going to have any this week, don't you worry, they'll come back. But next week we're going to do a lab, and I've told you a couple of times already, we're going to go through different types of reactions in lab and see how they actually happen. We'll do some acid-base reactions, we'll do some precipitation reactions, we'll do some oxidation-reduction reactions, we'll do exothermic reactions, endothermic reactions. Okay? All right. So now we're going to work on balancing the following equations. I'm going to give you one, and I want you to take a couple of minutes and try to balance this yourself. Okay, so the equation is methane, CH4, and oxygen react to form water and carbon dioxide. take a couple minutes and try to balance this on your own. Maybe another minute or so. All right, so I told you that I would give you some additional advice or some additional tools that aren't written on the slide. But one of those, the rule said to basically start with the element that is most out of balance. But a piece of advice is to avoid starting with an element that appears in more than one molecule on either side of the arrow. Okay? Avoid starting with an element that appears in more than one molecule on the same side of the arrow, because that one's a little bit messier. All right? So how many carbon do we have on the left? One. How many carbon do we have on the right? Also one. Okay, that's already balanced. How many hydrogen on the left? Four. How many on the right? Two. That one is not balanced. How many oxygen on the left? Two. How many oxygen on the right? Three. That one is not balanced either. 2 and 3 is more complicated than 2 and 4. But again, we're not going to start with one that appears in multiple molecules on the same side. Oxygen is here and here in 2 molecules on the same side of the arrow. So we're not going to start with oxygen, which leaves us only with hydrogen because that's the only one that's out of balance. That's not in multiple molecules on the same side. Do you agree? All right, so we have 4 hydrogen on the left. We have 2 hydrogen on the right. What is the least common multiple of 4 and 2? 4. How do we get 2 to equal 4? We multiply it by 2. The only way to do that is to put a coefficient of 2 in front of H2O. How do we get 4 to equal 4? Yeah, multiply it by 1 or leave it alone, right? It's already 4. Okay, so we'll leave this alone. Now, how many carbon do we have on the left?
1.
Still 1. How many on the right? 1. How many hydrogen on the left? 4. How many hydrogen on the right?
4.
Now 4. How many oxygen on the left? 2. How many on the right? 4. Okay, so we've got to fix that problem. We've got 2 here, and we've got 4 here. What is the least common multiple of 2 and 4? 4. How do we get 2 to equal 4? We multiply it by 2. Did you say multiply by 2? Oh, I thought you said divide by 2. Yeah, I got all. Anyways, and 4 times 4, I mean, that already equals 4. Yeah.
Do we have to include the oxygen in CO2 in this count?
We do, yeah. So there are 2 here, and then there are 2 more here. So for a total of 4. But yes, absolutely. You have to count the total amount on either side of the arrow. Okay, we already know that carbon was balanced before and we haven't changed the number of carbon at all, so that's balanced. We haven't changed the number of hydrogen at all, because all we did was add a coefficient to a molecule that only has oxygen, and we know we just balanced oxygen. And so now this entire reaction is balanced. Right? Okay, so remember I give you another piece of advice. Don't start with an element that exists in multiple molecules on the same side. All right, now let's do this one. This one you don't have to work on by yourself to begin with. We'll start this one together, we'll work on it together, and we'll finish it together. All right. C6H12O6. Where have we seen this before?
Glucose.
Yep, we worked a problem where we made a glucose solution. Maybe glucose, could be fructose. So we'll call it glucose reacting with oxygen to form water and carbon dioxide. And looky here. The products are the same as the previous reaction. Do you find that interesting? I find it a little bit interesting. And the reason why is because these are the same type of reaction. They are both examples of combustion reactions. Combustion reactions, where you are burning something in the presence of oxygen. Okay? In this case, we are burning methane in the presence of oxygen. In this case, we are burning glucose. And this is a reaction that happens in our cells, although it's not rapid, it's slowed down so that you're not releasing an enormous amount of heat all at the same time. Otherwise, your cells would catch fire, which would be awesome, but would not be very helpful to keep your cells alive. But have you ever noticed water pouring out of the tailpipe of a car? So notice water is a product of a combustion reaction. So in an internal combustion engine, you are burning gasoline, and the products are carbon dioxide and water. And so if it's cool enough and the exhaust is not heated up and the water doesn't vaporize, it'll pool and dump out the back of the tailpipe. Now once the exhaust gets nice and hot, the water will vaporize and it'll come out as water vapor. And you won't see it unless it's really cold and it starts to condense, and that's where you get like that mist that happens when you breathe when it's cold. So water vapor starting to condense. It's kind of cool. All right. All that to say, let's work on this problem. How many carbon do we have on the left? 6. How many on the right? 1. That one is not balanced. How many hydrogen on the left? 12. How many on the right? 2. Also not balanced. How many oxygen on the left? 8. How many on the right? 3. Sorry. 3. Also not balanced, but we don't want to start there because oxygen appears in 2 molecules on the right and 2 molecules on the left. That's messy. So let's start with carbon or with hydrogen. Okay, what do we choose? Carbon or hydrogen? Carbon. Okay, so we've got 6 carbon on the left. We have 1 carbon on the right. What is the least common multiple of 6 and 1? 6. How do we get 1 to be 6? Multiply it by 6. The only way to do that is to put a coefficient of 6 in front of CO2. And now we know carbon is balanced, right? Because what do you do to 6 to get it to be 6? You leave it alone. I mean, you can multiply it by 1 and put a 1 in front of glucose, or you can just leave it alone. It's already 6. Okay? So we've balanced our carbon. We have not done anything to hydrogen. All we did was put a coefficient of 6 in front of carbon dioxide. There's no hydrogen there, right? So we have not adjusted our number of hydrogen. So we still have 12 hydrogen on the left. How many on the right? 2. What is the least common multiple of 12 and 2? 12. How do we get 2 to be 12? Multiply it by 6. The only way to do that is to put a coefficient of 6 in front of H2O. How do we get 12 to be 12? It already is, right? We'll leave it alone. And now all we've done, we have not changed our carbon at all. So, I mean, we can count it if you want. We've got how many carbon on the left? 6. How many carbon on the right? 6. How many hydrogen on the left? 12. How many hydrogen on the right? 12. We're good, and now we need to balance oxygen. And we didn't want to start with oxygen, but now we've got to balance it. How many oxygen do we have on the left?
8.
Still 8, which is what we started with. How many do we have on the right?
24.
We have 6 times 2 is 12. 6 times 1 is 6. 12 and 6 is 18. Now, another piece of advice. Another piece of advice is when you have an element that is in multiple molecules and your numbers are really big and complicated, don't be so quick to try to find the least common multiple. See if there's another way. Okay? And looking at this, because if we want to do the least common multiple of 8 and 18, it took me 3 times to get this on Monday, because Mondays are not great for math for me. I don't know if I mentioned that to you before. Those of you that are usually here on the Monday section, my mental math is really bad on Mondays. But the least common multiple of 8 and 18 is 72. That's complicated, right? So let's not be so quick to do that. Let's see if we can balance this another way. Right now we have more on the right than we do on the left, right? Would you agree with that? So we can look to the left and see if is there a way we can add the number of oxygen that doesn't influence anything else. Yes, just like before, we have a molecule on the left that only includes oxygen. Meaning we can put a number in front of it and all it's going to do is change the number of oxygen that we have. It's not going to change anything else. It's not going to change the number of carbon we have. It's not going to change the number of hydrogen we have. Right? All it's going to do is change the number of oxygen. How many oxygen do we need on the left? 18. Why? Because we have 18 on the right, and the law of conservation of matter tells us we cannot create oxygen atoms. Okay? Right now, how many are there in glucose? 6. So we need 12 more from this oxygen molecule, right? We need 18 total. We have 6 here. We need 12 more. How many do we have right now? 2. How do we get 2 to equal 12? Multiply it by 6. And so we didn't go through the process of finding the least common multiple. But now we don't need to check carbon and hydrogen because we know putting the 6 here doesn't change those numbers. And we already have those balanced. Now let's check our number of oxygen just to be safe. How many oxygen on the left? 6 here, 12 more here for a total of 18. 6 here, 12 more here for a total of 18. And now it is balanced. So if you are going to burn 1 molecule of glucose, which maybe we'll do this next week, we'll actually do a combustion reaction with something that's pure sugar. That's fine. Did I tell you about the gummy bear before? I think we'll do a gummy bear combustion reaction. Anyways, so if you're gonna combust 1 molecule of glucose, you're going to need 6 molecules of oxygen. You're going to produce 6 molecules of water and 6 molecules of carbon dioxide. It's also going to be true for when this reaction happens in your body. You notice anything interesting about the products, knowing that this reaction happens in our body? So what does this mean that your cells are producing by carrying out these reactions? Yeah? Water and carbon dioxide. You're like, that's so cool. Our cells are actually producing water by breaking down sugar. And some animals that live in really dry environments, they do not drink any water. All of the water they use comes from combustion reactions. Kangaroo rats are that way. They don't drink any water. All of the water they get comes from carrying out these reactions. What's the other product? Carbon dioxide. So we require oxygen as a reactant, and then we produce carbon dioxide as a product. This is why we breathe in oxygen, and we breathe out what? Carbon dioxide. Look at that. Tying this in to our biology. It's wonderful. You're welcome for that. All right, any questions about this one? This next one is good because it introduces something new that we haven't seen before. So we've got CaC2, which would be calcium carbide plus H2O, which is water, produces C2H2, which is dicarbon dihydroxide. And then plus calcium hydroxide. Do you see something new that we haven't seen before? Parentheses. And so the parentheses, what do you think this means? How do we handle these parentheses?
The 2 goes to both letters.
The 2 applies to both letters, to both elements. And I know what you're thinking, why don't we just write O2H2? And the reason is because this is also giving you an idea of how it's structured. It's structured such that you have the OH coming as a unit, functioning as though it were a single element, even though it's 2. And then we have 2 of those. These are hydroxide ions. We saw this last week, right? Where we said bases lead to the release of hydroxide ions. Do you remember that last week? Acids lead to the release of hydrogen ions. Bases lead to the release of hydroxide ions. This acts as a single unit, even though it's 2 different atoms. That's why we put in parentheses, but this number applies to both. All right, so let's do this one together, and then we have the next one with some parentheses, and I'll have you work on by yourself for a few minutes. Okay? How many calcium do we have on the left?
1.
1. How many on the right?
1.
Also 1. How many carbon on the left? 2. How many on the right?
2.
Also 2. Okay, so those aren't out of balance. How many hydrogen on the left? 2. How many hydrogen on the right? 4. Right? This 2 applies to both the atoms in here. So we have 2 here, 2 more here. That one's not balanced. But it exists in 2 different molecules on the right, so we don't want to start there. Unless we have to. How many oxygen on the left? 1. How many on the right? 2. That one's also out of balance, but it's only in 1 molecule on both sides. So we'll start there. We have 1 oxygen on the left, 2 on the right. What is the least common multiple of 1 and 2? 2. How do we get 1 to be 2? Multiply it by 2. The only way to do that is to put a coefficient of 2 in front of water. All right. Okay, so we know we just balanced oxygen, right? We know we put a 2 in front of something that does not have any calcium or any carbon, meaning we didn't change our numbers. We knew those were already balanced. So all we need to do is check the hydrogen. How many hydrogen on the left now? 4. How many on the right? 4. We balanced hydrogen and oxygen at the same time. Isn't that wonderful? 1 coefficient and you're done. Doesn't always work that way, but when it does, we smile, we appreciate it, and we move on. And we move on. Okay. Any questions on that one? You like those parentheses, don't you? Man, this is, this was getting to the point where it just seemed like the same thing over and over and over again. Dr. Engel, you added something new, flavorful, right? Expanding my palate. I love it. Okay, so here's the next one. And I want you to work on this one for a few minutes and see if you can come up with the balance. So barium carbonate plus this one nitrate. This is nitric acid. Produces barium nitrate carbon dioxide, and water. Can you see the water, Tom? How about now? Yeah. And I know it was written on the board, so I didn't have to write it, or it was written on the screen, but I wrote it anyways, because we're going to balance it together, and I can't write on the screen, fortunately. All right, take a couple of minutes, see if you can balance this. All right. Do you need some more time? Okay. Do one more. Okay. How many barium do we have on the left? 1. How many on the right? 1. Already balanced. How many carbon on the left? 1. How many on the right? 1. Already balanced. How many oxygen on the left? 6. How many on the right? 9. Not balanced, but complicated. How many nitrogen on the left? 1. How many on the right? 2. Not balanced, but not so complicated. So only 1 molecule on the left, 1 molecule on the right. And what about hydrogen? How many on the left? 1. How many on the right? 2. Also not balanced, also not complicated. 1 molecule on the left, 1 molecule on the right. So we have hydrogen and nitrogen that are good candidates to start with. Oxygen isn't balanced, but we don't want to start there because it's complicated. Which one do we want to go with? Hydrogen or nitrogen? Hydrogen. How many hydrogen on the left? 1. How many on the right? 2. What's the least common multiple of 1 and 2? 2. How do we get 1 to equal 2? Multiply it by 2. How do we get 2 to equal 2? It already does. We leave it alone. Okay, we did not change our number of barium nor our number of carbon. We don't need to check those. We did change our number of nitrogen, but we know or hydrogen, we did hydrogen. But we already balanced that, so let's check our number of nitrogen. How many nitrogen on the left?
2.
Now there are 2. How many on the right? 2. Nitrogen is now balanced, right? We balanced hydrogen, which also balanced nitrogen. Now let's check our number of oxygen. How many oxygen on the left? 9. 3 here, 6 more here for 9. How many oxygen on the right? 6 here, 2 more here is 8, 1 more is 9. We balance hydrogen, nitrogen, and oxygen by using one coefficient. These are the best kinds of problems. Doesn't it feel good when you balance these? It just feels good to me. Maybe even great. You want to hear something sad? My kid's betta fish died today. And the only one that knows is our 3-year-old, because she was home when we discovered it. The other 2, it was still alive when they were getting ready for school this morning. They don't even know yet. They're going to be getting home from school in like 30, 40 minutes. And but I won't be there yet. So mom gets to handle that one. But at the same time, the last 2 ants that were alive in our son's ant farm, they died as well. Same day, all of their pets died. Those are the only pets we have too, because they're simple pets, a betta fish, and an ant farm. That's it. We lost them all. It's a bad day for my children. You might, if you think about them, pray for them. So, our oldest, she's 7. She's emotionally unstable as it is. She's an emotional wreck. All right. So see if you can balance this one on your own. Take a few minutes, work on this one, see if you can come up with a good way to balance this. Zinc hydroxide plus sodium hydroxide reduces sodium. I don't even know what the name of this would be. I don't even know. And water. I would call it sodium zinc oxide, but I don't know if that's what it's called. in another minute or so. Alrighty, how many zinc do we have on the left? 1. How many on the right? Also 1. How many sodium on the left? 1. How many on the right? 2. So that one's not balanced and not incredibly messy. How many oxygen do we have on the left? 3. 2 here, 1 more here. How many on the right? 3. 2 here, 1 here. So that one actually is balanced. How many hydrogen on the left? 3. And how many here? 2, but it's a little bit messy over here, so we don't want to start with hydrogen, but it's only hydrogen and sodium that are out of balance. So we'll start with sodium. Sodium has 1 here on the left, 2 on the right. What is the least common multiple of 1 and 2? 2. How do we get 1 to equal 2? Multiply it by 2. Okay, how do we get 2 to equal 2? It already does. We'll leave it alone. Okay? And so we know we've changed sodium, but we did it in such a way to just balance it. And so now let's check hydrogen and oxygen. How many hydrogen do we have on the left now? 4, right? 2 here, 2 more here. How many hydrogen on the left? Only 2. Okay, so it's still not balanced. Okay, how many oxygen on the left? 4. How many on the right? 3. Okay, now oxygen is not balanced. We unbalanced oxygen in our effort to balance sodium. Okay? Now oxygen is very complicated because it's in 2 places on the left and 2 places on the right. Do you see that? Hydrogen is in 2 places on the left, but it's only in 1 place on the right. Okay, so we'll start with hydrogen because that one is less complicated. How many hydrogen are on the left? 4. How many are on the right? 2. What's the least common multiple of 4 and 2? 4. And I know I gave you a rule that said when it's in multiple places, don't be so quick to do it this way. But in this case, the numbers aren't that complicated, right? It's not 8 and 18 like it was before. How do we get 2 to equal 4? 2, and that's simple because it's only in 1 place. Right, on the right side where we need to add more hydrogen, our hydrogen is confined to a single molecule. So the only way to do that is to put a 2 in front of water. Now we know we've balanced hydrogen, right? Because now we have 4 on the right and 4 on the left. We haven't changed our zinc or sodium at all. So the only thing we need to do is change our oxygen or check our oxygen. How many oxygen on the left? 4. How many on the right? Now 4. So we balance both oxygen and hydrogen by adding a coefficient of 2 in front of water. Alright, so this one is a little bit more complicated than the 2 that came before it, where we only needed 1 coefficient of 2 to balance it, but it's still very, very manageable, very doable. Okay? I have one more I want you to work on, but before I do that, I want to tell you, so I passed your work back, and I already mentioned to you that before we do another big turn-in, I'll give you a folder that has your name on it, that you can turn in all of the material, and I'll pass it all back in. But I want to tell you, if you got anything on the exam that you were not happy with, or you need a detailed grade report, let me know. If you need a detailed grade report, I'm happy to get that to you. For if you needed to turn in to the entity that issues your grades, let me know and I can do that. It's no problem. And then if you are unhappy with your exam grade, let me know. Send me an email or have your parents send me an email or let me know before you leave. And I will print out a copy of the exam. And next week I'll hand it to you again in a sealed envelope. but between now and then, you can take your exam that I handed back to you. You can look it over. You can see what you did wrong, figure out a better way to answer those questions. But when you actually go to take the exam, you cannot have anything in front of you. You can't have your old exam, you can't have notes. You just have to be able to prepare for that before you retake it. Okay? Does it make sense? So regardless of what your grade was, unless if it's -0 and you got a 30 out of 30, you cannot retake the exam. Okay? But even if you got a 29 out of 30 and you want to retake it, let me know and I can make that happen. Okay? I'll tell you, there's really no need to retake it if you got a 29 out of 30, because 1 point is not going to make a big difference in your grade. But if it makes you uncomfortable, I understand that. We can fix that. Okay? Again, I'll tell you, there's no need for you to redo it as far as your grade is concerned. If there's an emotional need, I understand. All right? At some point in my life, I don't remember when it happened, I learned that as far as a grade is concerned, a 90% is just as good as a 100%. Okay? I learned that as far as your grade is concerned. Now, I know then you're like, yeah, but it's not a representation of the best that I could possibly do. I understand that. But at the time you took that test, it may have been the best that you could do. And so if you want to leave it, by the way, I'm not telling you have to redo it. So even if you got something that's like a -9 or a -6, which would be like a 21 out of 30 or 24 out of 30, you don't have to retake it. I will send out an email with all of this information, including the website. But if you want to access our course, our digital classroom, I'll give you the link for it. Those of you that accessed it last year, it's the same link. And if you were in the class last year, your login credentials from last year will probably still work to get you access to this year's, and you'll just have both classes in there. If it doesn't work to get access to this one, and for those of you that this is your first year, your login, your username will be your first initial, followed by your last name, and then 1819 for this school year. That'll be a username, and then your password will just be password until you change it. Okay? But again, if you already had login for last year, it should work, because for most of you, I just pulled your information over and enrolled you as a student that already existed. But for some of you that even were in the class last year, I created you a new username, which is first initial, last name, 1819. The exception are, I don't think, you guys obviously can't both be the first initial, last name, 1819, because your initials are the same. And so hopefully your credentials work. If not, I'll just look up what your username is and make sure you get that. All right? Okay. And again, I'll send that out as a reminder in an email. Oh, somebody from the Monday section that was in the class last year asked if I still have your work from last year that you turned in the last packet. If you didn't come pick that up, I'm going to bring it next time, and I'm going to give it to you. You don't have to keep it if you don't want to, but I'm going to give it to you. All right? Cool. Last problem. So go ahead and take a couple of minutes, work on this one. Nitric acid reacting with diphosphorus pentoxide to produce dinitrogen pentoxide and phosphorus acid. Alright, I know you may still be working on this, but I want to make sure we have a chance to conclude this. How many hydrogen do we have on the left? 1. How many on the right? 1. How many nitrogen on the left? 1. How many nitrogen on the right? 2. That one is not balanced. How many phosphorus on the left? 2. How many phosphorus on the right? 1. How many oxygen on the left? 8. How many oxygen on the right? 8. So the only 2 elements that are not balanced are nitrogen and phosphorus, both of which are contained to a single molecule on either side. So it really doesn't matter which one we start with. They're equally out of balance and equally complicated. All right, which one should we start with? Let's do nitrogen. How many nitrogen on the left? 1. How many nitrogen on the right? 2. What is the least common multiple of 1 and 2? 2. How do we get 1 to equal 2? Multiply by 2. The only way to do that is put a coefficient of 2. Alright, now we'll go to phosphorus. We didn't change our number of phosphorus, so we know it's still unbalanced. How many phosphorus do we have on the left? 2. How many phosphorus on the right? 1. What is the least common multiple of 2 and 1? 2. How do we get 1 to equal 2? Multiply it by 2. Alright, now we'll check. Again, we didn't change our nitrogen, so we know that that is still balanced. We just balanced our phosphorus. So now let's check our hydrogen. How many hydrogen on the left? 2. How many hydrogen on the right? 2. How many oxygen on the left? 11. 6 here, 5 more here is 11. How many oxygen on the right?
11.
Also 11. So everything is now balanced. Nitrogen is balanced, phosphorus is balanced, hydrogen is balanced, oxygen is balanced. Alright? That is our last problem, and we are out of time. So again, if you handed something in that I did not give back to you, feel free to come and look through